Hello everyone, Gigaraptor here again, coming at you with another tutorial where we will be covering the terminal velocity of an object, at least in an environment with air. So, how terminal velocities work is if you were to drop, say you were to drop a, I don't know, say you were to drop Nigel Farage from a plane. Let's say he's got a weight of about 75 g-newtons. So, you've dropped Nigel Farage from a plane. He's falling quite quickly, and he's accelerating very quickly. And initially, when he falls out of the plane, he's falling at with a full resultant force equal to 75 g-newtons. However, since there is air in our atmosphere, believe it or not, it causes a little thing called drag or air resistance, which applies in the opposite direction, and this increases over time as speed increases rate. So, say maybe 5 seconds into Nigel Farage's death plunge, he's still falling with at the rate of this force here, 75 g. However, he's also got this little force up here called air resistance, based off his volume. So that could be any number really. It really depends on the volume of the person. So it could be anything. Let's say 10 g-newtons. So that's basically what it is, and it increases over time. So you could fall any sort of distance before it reaches that. So what happens is that it will eventually let me compose myself. When our air resistance equals our weight, it will stop. It will reach our maximum. So the maximum sort of air resistance that Nigel Farage can have is 75 g because of Newton's third law. I call it max. So once Nigel Farage has finished falling from his plane, once he's finished falling, it will reach 75 and he will accelerate no more, because as we learnt under Newton's first law, when F-res equals 0, acceleration is 0, because mass generally remains constant. Although I can imagine he probably avoided his vowels at some point, especially if they threw him out without a parachute. So yeah, so let's have an example. Say potato falls out of the plane. He has a weight of, say, I don't know, how much does a potato weigh? Say 1 g. Damn, I shouldn't have done that. No, potato, Elliot. Potato. Potato. So say our potato has a weight of 1 kilogram, so it's a big potato. What would its maximum air resistance be? It would obviously be 1 g, so it would be g-newtons maximum. I'm not going to talk about rates of building up or anything, because from what I've studied thus far of the curriculum I'm kind of teaching here, it doesn't really detail their resistance, and a lot of the time when you're doing calculations you will be told there is negligible air resistance. Although if we were to get out a velocity time graph, say I'm going to call this V, we've got our distance here, so it's a d meters. Without air resistance, what you'd probably expect to see is, before it hit the ground, you just go like that. Because there's no air resistance, therefore, actually that was BS. Ignore what I just said. I just realised I was wrong. So let's just do a graph here. So distant meters. It's been a long day. So Since there is no air stopping it, there will be no decrease in acceleration. It'll just go like, it will increase proportional to, like, because like A equals F over M. So since mass will remain constant and the resultant force will remain constant because there's no air resistance, it will just have a constant gradient here until obviously someone hits the floor. So like that. Let's say it was marked reckless. So it will just go like splat. However, I'll differentiate them here. So I'll say, what's the value? So say AR. However, if we've got AR here, I'm going to draw that up here. Oh, that didn't look particularly good. I'm going to go get rid of that. Let's make it bigger. I'm going to do distance, meters. And probably make that look less like an A. So, -1. So, when the person initially falls from the plane, it's going to be pretty much no air resistance. So it's going to be constant for a bit. However, as air resistance increases, it's going to sort of peak out a little. That I should probably make it look like a little bit flatter until it reaches 0, which this is the point where AR equals mass. This is assuming no one's pushing him, so, and it will just remain like this because there's a constant velocity now because F-res equals 0, and under the first law, like, if there's no resultant force, there's no acceleration. So until the person hits the ground, so splat. Shouldn't have gone back there, but you know, it's all in the wrist drawing. If any artists are watching this, so splat. So that was air resistance. Thank you for watching, and I hope there were no UKIP supporters here. Well, might have to edit that out now. Yeah, so I'll see you later on the next tutorial, which we will be covering. I think I know what we'll cover. We'll cover significant figures because we came across quite a large issue here. So, like in earlier tutorials with it. So I think it's probably a good idea to cover it. All right, I'll see you later. Goodbye.